Welcome everybody. So today we will have 2 half-hour talks, and the first speaker is Azouri, who will talk about Motivic nearby cycles and quadratic conductor formulas. Please, Ron.
Yeah. Hi, so thank you for inviting me, and I'm glad to speak in this seminar. So what I'll talk about, I'll report on 2 recently published things on the archive. One is the Euler characteristic of homogeneous and quasi-homogeneous hypersurfaces by Levine, Pepin Lehalleur and Srinivas. And the other, which I will more concentrate, is the quadratic Euler characteristic of nearby cycles and quadratic conductor formula by me. So generally, the general geometric question maybe is we want to study singularities in general, and singularities which are the generation of smooth families, meaning that we have a scheme X over a base S, and we have something that we call a special point or special subscheme, generic point. The generic fiber is usually a smooth family, but the special is probably has singularities, and we want to study them that way. So just maybe a very simple example is if we have this question, this function, the example here, then the fiber over anything which is not 0 is a smooth scheme, but over 0 it's not a smooth scheme, and studying the whole family can let us learn some stuff about the singularity. So this example, the base is A1, the generic fiber is GM, but we will concentrate in a local setting when we take the base S to be the spec of a discrete valuation ring, and then the generic fiber is defined by K, the fraction field, and here we have the residue. So that's the general setting, and we want to understand motivic tools to study. So let's see what in the motivic world we can see in this situation. So the first tool is the functor defined by Ayoub of nearby cycles. So what are nearby cycles? So, well, it has some, maybe the history is from Milnor, from complex manifolds. We can take the Milnor fiber, taking T defines maybe a small circle around the singularity, which is 0, and we take this, intersect with a small ball, and take the cohomology. Typically, it's a wedge of spheres, and then it can teach us something. So if we take this, we get a sheaf usually on the special fiber. So in the context of algebraic geometry, it's due to the Levine, there is a Tal version for the derived category of practical sheaves. There's a functor from the category of X eta to the category of X sigma, from the generic fiber to the special fiber. And Ayoub defined the formalism in a Motivic homotopy theory version, which is more elaborate to define, but it still satisfies some formal properties. So it's a functor from SH of X eta to SH of X sigma. Some of the properties, or the most important properties that we will mention today, is first, we want to compute it. So how can it be computed? So it can be computed on restriction to smooth pieces of a reduced normal crossing divisor, X sigma. That means that if X sigma is a reduced normal crossing divisor and we have some smooth piece, something inside, then we're in good shape basically to compute it. And okay, just some other properties is that psi ID is monoidal, important. Okay, it has some shift properties. Okay, that's quickly about this functor. Another two is still different or coming from a different theory of Motivic integration. There is a definition of Motivic Milnor fiber in the Grothendieck ring of varieties, which goes as follows. So suppose we have a log resolution, meaning that we can somehow replace X by Y with Y sigma, which is a simple normal crossing divisor. And then we write Y sigma with the composite two components. Di are the components, and for a subset, we define Di to be the intersection of the Di components. Di circle is we remove the intersection with the other components. So in the setting of this theory, Denef and Loeser defined some certain coverings of this Di. So these are the coverings. There are some étale covering of Di circle. Tilde is an étale covering of Di circle of degree, the GCD of those Ni's here. And from the Motivic data function in the context of the Grothendieck ring of varieties, they define this alternating sum. This Di tilde is the class of the covering, and L is the class of A1 in this ring. We can take this alternating sum, which it may seem very different than the first two, but actually it's much connected. So Ayoub, and Sebag proved this thing for semi-stable schemes is the same as the class of psi x, Ayoub's functor. So that's that too. And another idea how to understand this, maybe enumerative tool, is just to use this famous topological invariant of the Euler characteristic and look at the difference between the Euler characteristic of the generic fiber and the special fiber. That's some invariant that may help us if we can express it as some way expresses with invariance of the singularities of X sigma, then this can be called a conductor form. So that's the aim, and okay, we can do it purely topologically if we have something over C, but we want to talk about a Motivic version. So for the Motivic version, we'll take the Motivic version of the Euler characteristic. So that's the Motivic version. We try to be the Motivic Euler characteristic, which
Actually, would you scale up a minute so that I could see the conductor, the right-hand side of the conductor is the difference?
Sure.
I see, great, Thank you.
Yeah, so it's I just want to express it in terms of invariance of singularities of x. Okay, no, it's not equal to invariance. I want to express it somehow. Yeah, so that's it. Also, we'll take the Motivic Euler characteristic, and in this setting, we'll take a variant of it, the compact support version, which is good for defining of a singular scheme. So say that we have a scheme over a perfect field, which is of finite type and separated. And we take P lower shriek of 1x, the motive of x with compact support. If it's a dualizable object, for example, in the case of a smooth and proper scheme, then we have a map from the unit to this unit map and co-unit map. And here we can change the order. This composition gives us an endomorphism of the unit, which we call the Euler characteristic of x. If we do it classically, maybe in the category of vector spaces or the derived category of vector spaces, we get the usual Euler characteristic there, and also in the topological setting, it can be defined that way. But here in our category, in SH of K, the endomorphism ring of the unit, as you may know, is equivalent to the Grothendieck-Witt ring of the unit. So in fact, what we get is something that can be expressed in quadratic form instead of just integers in this setting. And we can also recover the usual Euler characteristic from it, the topological one. If our field is embedded in R or in C, we can treat the characteristic by the rank and the signature. The rank will give us this Euler characteristic. But what is nice with this compact support version is that it satisfies a cut and paste formula. If we can compose X to an open and closed subscheme, then we can paste it that way. And that allows us to define it also for non-smooth, to extend from this definition, from this object that we know are dualizable, at least in characteristic 0, we can define it for every finite type and separated scheme.
Does it satisfy an inclusion-exclusion type formula when it's not a disjoint union?
I think so, because you can just get it from, I mean, okay, I'm not sure. I'm not sure about, but I mean, yes, as long as it follows from this formula, then yeah. If not, then I'm not sure.
I think it's stronger than that formula, but
Yeah, I'm not sure. Yeah. Well, it's just there is this distinguished triangle, and then it's some properties. So the category is formalism of the functor. So that's how it follows. Okay, and then what is the quadratic conductor formula for hypersurfaces by Levine, Pepin Lehalleur and Srinivas? So the setting, the assumptions, O is a discrete valuation ring, K is the fraction field, the residue field, T is a uniformizer, which we fixed. F, a homogeneous polynomial of degree E, which defines a smooth hypersurface over K in P and K in the projective space, and E and the characteristical co-prime. Then we consider H, which is the projective scheme defined by this polynomial in the projective space. So if we take t equals 0, we get, okay, so let's look at the formula. So I have chi of ht, and I have chi of h0, so that's the singular fiber, and that's the generic fiber. And so first, okay, so let's just see what h0 is. H0 is, if I put here t equals 0, just defined by f, but I have an extra variable, so it's a projective cone on Pn. And at 0, it may have a singularity. And ht is smooth for t. Now I can compute the other characteristics, but the problem in this, the problem or the difference from the classical theory is that they are not integers and they live in different rings. One lives here over the residue field and one lives here over the fraction field. But there is a specialization method. Algebraically, it's just to put t equals 1. So that's the difference we're going to compute. I denote it by delta t of f. And the formula says that it equals this thing on the right-hand side. So let's see. So that's e minus 1. Its parentheses mean the quadratic form of e. Like x goes to e, x squares to x squared. So we have this difference plus minus e to the n times this invariant, which is called the local Euler class. And in fact, algebraically, it's a certain quadratic form defined by the Jacobian ring. That's the Jacobian ring. And then it's called the Shea-Torch quadratic form, and we just define somehow algebraically. It also has a geometric meaning. So, well, that's the formula. I just explained the terms. Okay, how it extends a classical formula, then over C, this is, we have the rank here. So this is the Milnor number, and this is formula by Milnor. Now the thing is that over C and over R, this term vanishes. So this term is something new in the Motivic version. Well, the idea of the proof is to compute those terms using the Motivic-Gauss-Bonnet formula and express the Jacobian ring in terms of Hodge cohomology. Okay, so I gave you the version for a homogeneous hypersurface. There is a weighted homogeneous version. If there are weights, just a bit more complicated, but very similar. So that's the formula in this paper. Now, we want to extend it to a more general setting. So that's the aim. in a way, make this formula a local formula and extend it to a more general case. So let's see what's the case. So F over spec O is a flat proper scheme. It's smooth over the base field, and also the xk, the generic fiber, is over k. The characteristic has to be 0 in this case, so maybe in a way it's less general. And we assume that the special fiber has a few isolated singularities, more than one, which in a way, in each of them, the scheme looks similar to the first case, to this case. So in that sense, I mean, make it a local formula. And for each point, we can resolve the singularity by blow-up. And we have this assumption that the intersection of what I denote by D1, the exceptional divisor, and D2, the strict transform in the blow-up is transversal. This is equivalent to, I can say it differently, that if I look at the stock at a point P, note by S0 to Sn, a regular sequence generating the maximal ABL, I can write the function f star of t as a homogeneous polynomial of degree E plus something in higher degree, where the f in the projective space over the residue field is smooth. So these two conditions are equivalent, but this looks very similar to the case we just discussed before. So in that sense, I say that X looks at P like a homogeneous singularity defined by a polynomial F, which is this polynomial, this condition. And then the main theorem actually compares delta T of F, which I remind you is just this difference in this formula, be defined for any polynomial F at a point P, so that for each singularity P, according to this condition, there is some polynomial F that we can assign to it. So if we take this difference, it's the same as chi of the psi F at the point P minus 1. In a way, maybe we can look at this as something measuring the vanishing cycles for X locally at P for the scheme X, and this measures it for HF, this hypersurface from the previous slide. In fact, they give us, although these are different schemes, they give us the same thing. Well, so that's the theorem, and I'll just talk about a bit in a few minutes about how to prove it. So we want to compute this thing. We can compute it by pieces. How can we do it? If we reduce X to a scheme Y with reduced special fiber and smooth pieces. So, well, just reduction, assume it's a local formula, so assume that P is the only singularity and look at the local case, so take off the stock, and we make the following construction. That's the construction. First, we blow up at the point. After that, we base change by E, taking an if root of T, and after that, we normalize. We get a scheme Y, which in this case gives a semi-stable reduction for X, meaning that Y sigma is reduced. So if we look at the first step after a blow up, X sigma has two components, D1 and D2, the exceptional divisor and the strict transform, and their intersection. And if we go through this process, then the coverings that we get, the one tilde and the 2 tilde are smooth, and we get a reduced special fiber. So that's stable reduction. Moreover, we can compute these D1 tilde and D2 tilde, give these formulas for what there are in the projective space. So, and this all follows from local computation with the blow up. So maybe I'll just do it quickly. So maybe if we can, so X tilde is a blow up, we can write it as approach the field with some parameters, and it's covered by affine pieces. So just for example, on U0, which is when T0 is not 0, we can write F star T, can take out S0 to the E. S0 to Sn were generators for the maximal idea. We can write it that way. So just locally on this affine piece, if I want to describe it, it is defined by T equals S0 to the E times U0. So from here we can see that we have two pieces and one has multiplicity E. So it's not reduced. After base change, so we change to T prime to the E. It's S0 to the E times U0. And then after normalization, it's the same as adjoin Tn plus 1, which is T prime over S0. And then we get something like T prime Tn plus 1 S0. It's a reduced, defines a reduced divisor when T prime is 0. And we can also see from here, if we just put this here, we can see the formula. It's Tn plus 1 to the E equals U0. That maybe hints how we get this formula, that D1 tilde is covering this formula. Okay, so that's a computation on which we compute these pieces, and we can compute the Euler characteristic by this reduction and by it on these pieces. Now let's see what we get. So we get from the property of Ayoub's functor that I told you, that it can be computable when we have a reduced normal crossing divisor. So we get that the Motivic Euler characteristic equals to this thing with these pieces that we computed. Now, well, this formula is in fact, it's just a special case of the formula that I gave you before. that I told you before about of Ayoub, Ivora, and Sebag. So in fact, we reprove here a special case of this formula when this construction gives us a stable reduction. Well, so we get this formula, but if we just look what are D1 tilde and D2 tilde, we express them just in terms of F. So that way we can compare it with the hypersurface defined by F. So let's see, so chi of D1 tilde is just, okay, I have to finish so quickly. Chi of D1 tilde is just this thing which looks like putting T equals 1. So it's in the hypersurface H, which I defined before. So that's just, this just equals this. And here, -1 is like A1. So this is like A1 times D1 to tilde. But I told you before that H0 is the projected cone of a D1 tilde. So if we remove that one point and use cut and paste, it's the same thing. So anyway, this computation by pieces gives us the comparison with the hypersurface H. And then we can just use the formula that I told you from the paper of Levine, Pepin Lehalleur and Srinivas, and get, just use it and get this more general formula, which looks like that. So yeah, basically I just told you everything about how to get it. Have this for X. We can just by the shift properties of psi Ayoub's functor, we can just separate it for this sum locally at the points, which I told you goes to this difference, which in the previous paper it is proven, and then we get this formula. And that's it.
Okay, thanks a lot, Ron.
Any questions?
I guess it's unclear what happens to more general types of singularities. Are there any guesses or formulas then?
Yeah, so the thing is that there is this E which appears here, which is like this term which appears here, which is relates to the degree of the homogeneous or quasi-homogeneous. Okay, this also extends to the quasi-homogeneous case. So so this really relates to the homogeneous, to having a homogeneous or quasi-homogeneous singularity. So in a more general case, when we don't have a polynomial with such an E, then it's supposedly something, has to be something else. So, yeah, it is interesting, but I don't know to say what can be done then.
Okay, thanks. Any other questions?
Yeah, is there, sometimes discriminants get defined as kind of an intersection in a moduli space of all hypersurfaces. You can intersect the spec of the O with the locus of singular ones, and that can be this, it can be called a discriminant, that sort of intersection. And there are equalities, both equalities and inequalities between conductors, the way you've defined them, and these discriminants. And so I was wondering about quadratic enhancements of relations between conductors and discriminants, where discriminant is some intersection between the singular locus of the moduli space of, say, hypersurfaces, or a moduli space of some kind of scheme that you're interested in, like the X and the spec O.
Well, so that sounds really interesting. I mean,
Awesome.
discuss it later if you have some. Then I'll be happy to discuss it.
Awesome. And if you run into Padma Srinivasan, she does this classically a lot. And yeah, thanks a lot. I really enjoy your theorems.
Okay, guys, more questions for Ron?
I mean, I guess one could ask if the weighted projective space could be replaced by a a toric variety or something.
But sorry, I didn't replace the projective space by
A toric variety?
toric variety. Yeah, I mean, yeah, I guess. Yeah, I haven't think of it. I haven't thought of it. I don't know what to say, but yeah, it's also it's certainly a thing.
It seems like the argument would work, right? Because you have a sort of single polynomial that, I mean, it's very similar to a weighted projective space in some sense. Anyway.
Yeah, so that may be, yeah, that may be the next step. Yeah. Yeah, I mean, yeah, this whole stable reduction process is very, in fact, very related to toric variety, possibly.
Okay, thanks.
Okay, great. Then let's all thank Ron again for his very nice talks.